Please raise your hand if you've heard of the incurable diseases cancer, HIV, and Ebola. How many of you have heard of the incurable disease mitochondrial DNA depletion syndrome? Thought so. I didn't even know what it was until I started with my project, but now I do, and here I am to teach you. But first, a little story. A 2-year-old girl presents to the hospital with muscle weakness and respiratory failure. She couldn't be diagnosed. A year later, she dies. The cause? Mitochondrial DNA depletion syndrome, also known as MDS. This child is not known. The actual prevalence of MDS is unknown, though 45 officially reported cases are known. So instead of babbling on about the 44 other cases, let me introduce you to a potential breakthrough. First, some background information. This is a mitochondria. It's sort of explained as a powerhouse of the cell. So in other words, it produces all the energy the cell requires. A common misconception around the cell is that the nucleus withholds all the genetic information, which is false. The mitochondrion and its mitochondrial DNA encodes for a small fraction of our genetic information in the form of a DNA molecule. This DNA molecule is built up of DNA building blocks that are freely available within the mitochondrion for it to use. Think of it as a pile of Lego. You can build whatever you want in whatever order you want with this pile of Lego. But what happens when this pile of Lego starts to run out? That is where MDS is introduced. So MDS is actually a group of genetic disorders caused by a mutation on a gene that balances the DNA building blocks. So if we have a mutation on this gene, what happens is that we won't have enough DNA building blocks in our cells, so DNA synthesis won't be able to occur. This is where my research project was introduced, since I investigated a specific gene called thymidine kinase 2, also known as TK2. So what is TK2? Well, TK2 is one of the most important genes in maintaining this balance. A mutation to it is one of the most deadliest out of all MDS. So what does it do? Well, it energizes the DNA building blocks so that when DNA synthesis is initialized, the energy is released and used to actually build the DNA molecule. So what happens when we remove TK2? Well, we won't have any energized DNA building blocks in our mitochondria, so DNA synthesis won't be able to occur. So what are the physical effects of this, you may be wondering? Well, as mentioned in the introduction, muscle weakness and respiratory failure are common. Though in mice, on the other hand, one has observed a severe decrease in fat, as you see here. Additional phenotype was an increased general heart volume due to the heart's inability to pump out all of the blood because it didn't have enough energy. So before I continue on to my specific research project, here's a too long didn't listen. I studied a sickness called MDS. It's caused by a fault in our genetic information that in mice degrades their fat. So why did I do this, and what purpose does it have? Well, I did this to be able to differentiate between human MDS and mice MDS and hopefully create a more correct mouse model for human TK2 MDS and facilitate for therapeutic strategies within the near future. So how this was done, you may ask? This was done using quite a complex method, but here's a simplified and summarized version. Heart tissue was extracted from 6 mice. Why exactly heart tissue was extracted is because heart tissue, or the heart was the most abnormal organ out of all organs in the mice. The heart tissue was later analyzed by using a qPCR machine. What a qPCR machine can do is analyze the gene expression that tissue expresses. So I took 3 heart tissues from MDS-affected mice and 3 heart tissues from a control mice. And now you're probably wondering, what did it show? Well, here's a heat map I generated. These 3 columns are the MDS-affected mice, and these 3 columns are the control mice. And then each row represents a individual gene that was analyzed, where the 5 first genes are fat-related metabolizing genes, and the 2 later genes are sugar-related metabolizing genes. So now you're probably wondering, what does this actually display? And funnily enough, it doesn't display anything. Or what it does display is that the heart isn't the cause. There's no abnormalities in the fat metabolism or the sugar metabolism within the heart. So now you're probably wondering, what is the cause? And I asked myself that exact same question. But I didn't have enough time to analyze this. So instead, I proposed a couple of theories. The first theory was that the liver or other fat-specialized metabolizing organs are compensating for the heart. This would mean that the liver would absorb fat from adipose tissue and metabolize it and use it as energy. Another theory was that the intestines were involved. For example, nutrition could just be passing through the digestive system without actually being absorbed. Or the mice could be eating less because they feel stressed. It could also be something completely different and indirectly correlated. But don't fret, it is actually quite major that the heart isn't causing the fat degradation, since the heart was the one that was observed to have the most abnormalities compared to other organs. This means that since the heart isn't causing the fat degradation, some other organ has to, and it's a wide system. So have we solved the problem? Is the next stop a cure? Not really, but this is still a major breakthrough in the initial mapping of MDS. And hopefully in the near future, we will be able to remove mitochondrial DNA depletion system from our list of incurable diseases. I'd like to finish off by mainly thanking my mentor, Professor Anna Carlson, for the immense support I've received. Additionally, I'd like to thank all the organizers at the Race for Excellence for allowing me to participate in one of the most unforgettable summers in my life. Finally, and last but not least, I'd like to thank all of our partners, especially Tekniska Museet and AstraZeneca, for making all of this possible. Thank you.